Hey, this is Dr. B, and here we have a practice test on buffers and solubility. In this particular case, a student is given a 100 ml solution that has a gram of acetic acid as well as a gram of sodium acetate. It's a buffer system, a weak acid and a conjugate base. Acetic acid has a Ka of 1.8 times 10 to the minus fifth. The pH should be roughly 5. Let's see how the Henderson-Hasselbalch equation works out. Since we'll ask several problems here, let's calculate how many moles of acetic acid. Well, 1/60th of a mole. How many moles of sodium acetate? 1/82nd of a mole. And since we have a tenth of a liter, the molarity goes up by a factor of 10 for each one. The negative log of the Ka is the pKa, which is 4.74. The concentration of the acetate is calculated as 0.121 molar. The acetic acid is 0.167 molar. This should have a pH of 4.6. The pOH would be enough to bring it up to 14, which is 9.4. The negative log of the 10 to the minus pH should give us the hydronium ion concentration, which is about 10 to the minus fifth. And these multiplied through to give you 10 to the minus 14th, which is the equilibrium dissociation constant for water. Or you could do 10 to the minus pOH, which we had up here. And we have about a 10 to the minus 10th molar solution with respect to hydroxide. If we wanted to bring the pH up by 1, let's leave out the concentration of acetate, since we need to add some more of that base, into the Henderson-Hasselbalch equation. There's the negative log of the Ka. X is our unknown. Solving. We subtract 4.74 from both sides, then take 10 to that power to get rid of the log. We find that we need a 1.209 molar solution of sodium acetate. Let's turn that into grams. Well, since 82 grams is a mole, and we have a tenth of a liter that we need, everything cancels nicely. We find we have 9.917 grams required to bring that pH up by 1 unit. However, don't forget we already have a gram in there, so we need to add an additional 8.92 grams of sodium acetate. The question's almost identical if we want to bring the pH down by a factor of 1. Here we solve for the acetic acid concentration. So we'll leave that as a blank. We've calculated the concentration of acetate in another problem. We're using moles per liter here. So X will be our concentration of acetic acid that we need. Solving as we did before, we need a 1.68 molar solution. Converting to grams, we note that we have a tenth of a liter solution, so liters cancels. 60 grams is a mole, so we need an additional 9.08 grams of the acetic acid. Minor typo here. This should be an H, this should be an H. This one's fine. Now, if we added 10 mils of strong acid to this buffer system, what would happen? Well, it depends if we've overwhelmed the buffer or not. Let's see if we're dealing with HCl be our limiting reactant, in which case the buffer is not overwhelmed. It'll react with the base, which is sodium acetate, to form acetic acid and water. And let's set up a nice table to see what we've got. There's quite a few things in this solution. We had 0.01 moles of hydrochloric acid, but we have a little more than that of the sodium acetate. So I like that. We have not overwhelmed the buffer system, but boy, there's not much sodium acetate left. This will increase the acetic acid concentration by the same amount. And all the HCl is gone. Most of the sodium acetate is gone. And the acetic acid concentration has gone up quite a bit. We can plug this directly into the Henderson-Hasselbalch equation, and we see we have a pH of 3.63. It went down as expected. If we add base to it, the pH should go up a little. And we probably do not have an excess of base either. If it did, we would just simply calculate the concentration of the base and find its molarity, and from that we can get the pH. Probably from the pOH first, right? And when you do those, be careful because you've added some volume to your solution, so incorporate that into your final volumes. But for this case, sodium hydroxide reacts with acetic acid to make sodium acetate and water. And when we set up our ice table, once again, 0.01 moles of sodium hydroxide, and more than that for the acetic acid. We do have some sodium acetate in there, don't forget about that. And all of the sodium hydroxide reacts with the hydrochloric acid, leaving us with only 0.0067 moles of acetic acid. That's what we're using here. Moles, not moles per liter. We have all the things we need to plug into the Henderson-Hasselbalch equation. Note that we're just using moles, but had we add liters, it would have canceled since it's the same amount top and bottom anyhow. And the solution went up by about 0.66 units, as we'd expect it to do. Now let's ask some solubility questions. We have 100 mils of an aqueous mixture that contains 1/10 of a gram of calcium carbonate, which is barely soluble in water at all. Let's find it out in moles per liter. Well, KSP is a funny beast. That number comes from multiplying out each ion. Since there's one of each, we can find the actual solubility from the KSP by taking the square root, and we find that it's about 10 to the minus 5th moles per liter. In grams per liter, we simply have to convert from moles to grams. So we have that many moles of calcium carbonate, 100 grams is a mole, and so we should have 0.00580 grams of calcium carbonate dissolving per liter of solution. The percent can be determined by taking a look at what's dissolved and comparing it to what's not dissolved. Well, if it's that many grams per liter and we have 1/10 of a liter, that shows that we have about 10 to the minus 4th grams of calcium carbonate consumed, and 0.1 gram is what we started with, so this is only 0.58% soluble. Now let's do one more determination and figure out, is that a saturated solution? I would say it sure is, since there'll be plenty of undissolved material sitting at the bottom. That means the solution that sits above that should be a saturated solution. Let's do it quantitatively. We calculated from the last slide that the water that we have would only have 5.8 times 10 to the minus 4th grams in it. And the remainder, the whole, almost a full 1/10 of a gram, would be sitting on the bottom undissolved. This is a saturated solution, and this is our buffers and solubility practice test.